Yeah, this is what we ended up with. Sorry, I had to milk the suspense there. Instead of throwing out the old magnitude system, which they realized didn't make sense, they put band-aids on it, and it still didn't make sense. And we're kind of stuck with it because they figured out that there were way too many stars in magnitude 1. Well, if you're already at 1, where do you go? I guess you can go to 0, but that wasn't even enough. So then they had to go to negative numbers. So the way to think about the magnitude, the apparent magnitude system, is to think of a number line. The more negative the number, the brighter the object appears. The more positive the number, the dimmer the object appears. So the brightest object in the sky is, of course, the sun. The sun has an apparent magnitude of about negative 26.5. The second brightest thing in the sky is the full moon. That has an apparent magnitude of about negative 12.5. Venus, at its brightest, is about negative 4.5. And you don't even get to the brightest star in the sky, nighttime sky, until you hit Sirius at negative 1.4. Now, they did at least keep that the dimmest that you could see with the unaided eye from dark skies to be a 6, like Hipparchus did. Gee, I sleep better at night knowing that one. No, you don't have to memorize these things, but you do need to understand the magnitude scale and be able to distinguish between brighter and dimmer things. The other confusing thing about the magnitude scale is that the difference from one magnitude to the next is not like twice as bright or 10 times as bright or some nice round number. It's actually the fifth root of 100. It's 2.512 something, 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 something. Yeah, confusing. But if we have two stars that look the same brightness in the sky, are they really the same brightness in reality? Because they could be very different distances away from us, right? And one could be cheating. One could be really close to us, and that's why it looks bright. And the other one is really far away, and so you can't tell that it's really a superstar. So if we look at the brightness of a star, how it appears, its apparent magnitude, we have to ask ourselves, are they bright because they're close, or are they bright because they're putting out more energy? And so we want to try to take away that unfair advantage. So let's imagine that we could place all of the stars exactly the same distance away from us, sort of in a lineup. And if we put all the stars the same distance away from us, those that look brighter are brighter. They're putting out more energy. So if we could place all the stars at one constant distance away from us, that would be something that we call the absolute magnitude. So apparent magnitude, or little m, is how bright they appear in our night sky. If we could place all of the stars the same distance away from us, that would be their absolute magnitude, which is big M. We're going to go back to the first unit we were talking about light. And remember that I introduced this mythical thing called the black body, the perfect emitter and perfect absorber. And I said there were two very important properties. Well, now's the time that we need them. The first important property is called Wien's law. It's spelled with a W. He was German. Have you ever asked yourself, how do we know the temperature of a star? I mean, we can't like shove a turkey thermometer into it, right? Well, we look at the light. And it turns out that bluer stars look blue because they emit more blue light than red light. Kind of makes sense. And on the other side, red stars look red because they emit more red light than they do blue light. Okay, that makes sense, but why do the stars do that? And what does that have to do with temperature? That's Wien's law. This is our friend the black body curve. Stars will emit over a complete range of wavelengths, but they will emit most of their light over one preferred favorite wavelength. And that preferred favorite wavelength is determined by the temperature. Hotter stars prefer to emit shorter wavelengths of light. They emit more blue light, they look blue. Hotter stars are blue-white. Redder stars are cooler stars. Cooler stars prefer to emit more long wavelength light, which is redder, and that's why they look red. And if you look at this diagram, you can see that the hotter star emits more energy overall, more light overall than this cooler star. So hotter stars are also brighter as well as bluer. And that brings me to the second great property of black bodies, the Stefan Boltzmann Law. The Stefan Boltzmann Law says that the luminosity, the total energy output of a black body, is related to two properties, its size and its temperature. And they're both important. Size is squared, and temperature is more important, it's to the fourth power, or squared squared. So written another way, the total energy output of a black body is the radius squared times the temperature to the fourth power. That means that bigger objects that have a bigger radius emit more energy, they're brighter, and also hotter objects that have a higher temperature are going to be brighter and emit more energy. And the great thing is that stars are a great approximation of black bodies. So we can use these relationships to relate the energy output or brightness of a star, its size, and its temperature. But we can get temperature from Wien's law, so we already know this. And we can get the luminosity. Remember, there's a relationship between the apparent brightness of a star, the true brightness of a star, and the distance to a star. Well, if we can measure the distance in some other way, we can work backwards and get the absolute magnitude or true brightness of a star, and we can use that to solve for how big the star is. So I've introduced the idea that some stars look brighter because they're closer, and some stars look brighter because they're putting out more energy. And so if we're going to talk about the true brightness of the star, if we're going to talk about the true energy output of a star, we need to talk about its luminosity. So let's go back and remember that when we were talking about black bodies, there were two properties of black bodies that were useful for stars. One was Wien's law, which relates the temperature to the wavelength at which it emits most of its light. And the other useful property was the Stephon Boltzmann law. The Stephon Boltzmann law, remember, related the radius or size of the star and the surface temperature of a star to its luminosity. So bigger stars are brighter, hotter stars are brighter. This relationship worked for all stars. But what we're going to introduce to you this week is another way of looking at the luminosity or energy output. And it depends on the type of star it is. So it's going to be sort of an approximate relationship. And this is going to be called the mass luminosity relationship. And I've given you a little preview here in this graph. Notice that these are log scales. Remember that back in the first lab, talked about reading log scales, okay? So this is not a log scale per se. This is the log of that which has been plotted. So the relationship, if you plot the log of the mass and the log of the luminosity, you get pretty close to a straight line. Low mass stars don't really work too well. And you'll see that it's a relationship to roughly the fourth power. So the idea here is more massive stars put out more energy. But there's a cost. If you're putting out more energy, that means you're generating more energy, which means you're using up your fuel faster. So what I'm also going to show you this week when we go through the math part in class is that the price you pay for being a heavier star, yeah, you put out more energy, but you're guzzling your fuel faster. You're a less efficient car, and so you're going to die faster. So the greater the mass, the greater the luminosity, the shorter the lifespan. And as I'll show you, it turns out that the lifespan goes like 1 over mass to the third power, which means that as your mass gets bigger, and this is a true log scale over here, and this is a true log scale over here, as your mass gets bigger, look at what happens to your lifespan. Your lifespan plummets. So low mass stars live much longer than the sun. They live for trillions of years, but high mass stars only live for hundreds of thousands of years. So you might think, oh, that's cool. Then stars want to be small. It's good to be small and conservative, and you can live for a really long time and you can laugh at all the high mass flashy stars. Well, it turns out that it's not too much of a good thing, it's too little of a good thing. If you don't have enough mass, you can't shine. Remember how the sun created its energy. Remember, the sun has nuclear fusion in its core. It converts hydrogen to helium. But you need a very high core temperature to do fusion. And the only way you get a very high core temperature is if you have enough mass to have enough gravity to squish your core to make it hot. If you don't have enough mass, you can't squish your core enough, you can't get hot enough, and you can't fuse. So there are objects that try to form stars that were too small and could never start nuclear fusion. And those are called brown dwarfs. We'll get to those later. Those are failed stars. Now remember that we had talked about the spectrum of the sun. Remember, these are the Fraunhofer lines. These are the absorption lines that we were able to use to figure out what the sun is made out of. Each one of these different absorption lines corresponds to a different element within the sun. We can do the same thing with other stars. It turns out that all stars are pretty much made of the same thing. But studies in the late 1800s figured out that stars of different surface temperatures had different relative strengths of their lines. So for example, all stars are made out of hydrogen, right? Mostly hydrogen with some helium and then other miscellaneous stuff. But for stars of a particular temperature, the intensity of the hydrogen lines varied. So there is a temperature effect on the spectrum as well. And when they first started looking at the spectra of different stars, they didn't realize that there was a temperature effect. So they just took a lot of photographs and they just started organizing them in order of the intensity of the hydrogen lines. And so the original system made sense. The letter A was the most intense hydrogen spectral lines. And at that point, they went all the way down to Q. Q was the less intense spectral lines. Well, after they improved technology, they figured out they didn't need that many letters. They figured out that some of those spectral classes, A through Q, some of those didn't exist. So they threw out the letters that did exist. Like there's no real star of a Q type. But then they realized that there was a temperature effect. And when they realized there was a temperature effect, they realized that not only did they have to throw out some of the letters, but they had to rearrange them if they wanted to order them in order of temperature. So they should have thrown the entire system out and started all over again. What did we learn at the beginning of this PowerPoint? Astronomers don't like throwing out systems. They like putting band-aids on them so that they can confuse astronomy students for the rest of eternity, right? Very, very sadistic. Annie Jump Cannon, realizing the politics of this whole thing, did not start from scratch. She merely threw out those spectral classes, threw out those letters that didn't exist, and rearranged the letters no longer in alphabetical order, but in order of temperature. Okay, and so here are the hydrogen lines that I've highlighted for you, and you can see that class A really does have the most intense hydrogen lines, but we no longer rate them by order of the intensity of their hydrogen lines. We rate them in order of temperature, and so we rate stars from hottest to coolest. And so if we look at the spectral classes in order from hottest to coolest, we end up with this, O, B, A, F, G, K, M. This was formally adopted around 1900, and we've been stuck with this sucker ever since. So how do you memorize O, B, A, F, G, K, M? People usually come up with horribly sexist acronyms trying to memorize it, you know, Oh, be a fine geek, kiss me. All right. Oh, be a funny geek, kick me. I don't care how you remember it, but unfortunately, it's really important, so you need to remember it, and it's a weird jumble of letters.